Hey everybody, it's Mr. Carr again. Today we're going to be looking at 1.5 day one here. The goal today is to start talking about identifying, graphing, and describing parent functions along with their transformations of the parent functions. Okay, so we talked already about what are functions and some of their graphs and some of their characteristics. So today we're going to be focusing on what's called parent functions. There's a wide variety of them. Okay, so let's start with this. A constant function has the form f of x equals c, where c is any real number, its graph is a horizontal line. Okay. When c is equal to 0, that is called f of x is the zero function. So what this kind of looks like would be like this. F of x equals, in this case, it looks like 1, 2, 3.5. Okay. That's the constant function. There's no other variables. It's just f of x equals a value. The identity function is f of x equals x. So this is our parent linear function here. So you see that it crosses at 0, 0, and it's just a slope of 1. A quadratic parent function is just f of x equals x squared. This is our basic version. It has the vertex at 0, 0. Okay, and it's going to be symmetrical about the y-axis. And we have our cubic parent function. F of x equals x to the third. Again, crosses at 0, 0. We actually have symmetry about the origin here. All right. So those are our parent functions. That's just some couple of things to look at to start. We also have a square root function. This is the parent function is f of x equals square root of x. It also passes through the origin 0, 0. And it looks like this here. Now remember what's happening with this one, the way it grows. We're taking kind of perfect squares. We can see where it crosses. So for example, perfect square of 4 goes up to a 2 here. Okay. And our reciprocal function has the form f of x equals 1 over x. So it doesn't cross through 0, 0, but it has origin symmetry around about the origin. Okay. Absolute value function looks like this. That's my parent function. F of x equals absolute value of x. We get a V shape with this one. It's also kind of split up as a kind of like a piecewise function that looks like this. F of x is equal to a negative x as long as x is less than 0. And it's f of x equal to x as long as x is greater than or equal to 0. Okay, that's where we get our V shape from. So the idea is if I go to, let's say, -3 here, it goes up to a +3. So it's kind of like a quadratic in a way. If I go to +3 here, still up to a +3 no matter what. Okay. All right. So we're going to describe some of the characteristics of our parent function. So we want to look at our reciprocal function 1 over x. Talk about its domain, range, intercepts, symmetry, continuity, and behavior and intervals on which the graph is increasing and decreasing. Kind of a lot, but let me just go ahead and do just a rough sketch of this one. As we saw from earlier, it's going to look like this and this. That's my reciprocal function right there. Okay, so domain. The biggest thing when I talk about this one is it is not going to cross 0 because that means that x value of 0 would cause us to divide by 0. So my domain is going to be any number I want except for 0. So I can write that as -infinity to 0 with parentheses, union of 0 to infinity. Range is going to do the same thing. If I kind of look at this one, there's nothing that I could take 1 divided by a number and I end up getting 0. So I got that horizontal asymptote as well. So that's going to be the same exact thing as domain. -infinity to 0, union 0 to infinity. It's the one value it's not allowed to be. Intercepts, because it can't be, I cannot plug in 0 for x and it never crosses 0. I actually have no intercepts at all. No x or y intercepts. Otherwise, I would plug 0 for x to find the y-intercept, 0 for y to find the x-intercept. Symmetry, we have symmetry about the origin. You can kind of test it out by doing this. Remember, testing symmetry, I could do f of like -x would look like this. It'd be 1 over -x. So f of -x, I can kind of rewrite it as the opposite of 1 over x. So that means it has symmetry about the origin. Let's see here. Yeah, symmetry about the origin. Okay. Continuity. We do have the infinite discontinuity right here in the middle at 0. Okay. So we have infinite discontinuity. Hope I spell that right. okay, at x equals 0. All right, we got end behaviors and increasing and decreasing intervals. And let me start with increasing and decreasing. I'll just put that over here a little bit. It is increasing. If we look at this one here, the graph is, as it goes left to right, is actually going down. And from here, it's going left to right, it's going down again. So technically speaking, this is always decreasing intervals. So there is no increasing, and it's decreasing on two different intervals. This is going to be from negative infinity to 0. It is decreasing here, and it's also decreasing from 0 to infinity. Okay, so two decreasing intervals and no increasing, because again, it's got to go left to right when we analyze that. And the last thing is going to be the end behaviors. We can kind of see here, I am approaching this 0 line from going both in negative infinity and to a positive infinity. So if I put that into limit notation, we'll say the limit as x approaches negative infinity, f of x equals 0. Okay. And the same exact thing when I go to a positive infinity. X approaches positive infinity, f of x equals 0. So, all the characteristics of my parent function there. Okay, so again, that's a bit of a review of our concepts of our characteristics of our functions. We can look at these same kinds of things pretty much every function. When we analyze our graphs, we look at all these characteristics and see what's there and what's not there and be able to describe them appropriately. All right. The next thing we're going to talk about is when we transform our graphs. So right now we'll talk about vertical and horizontal translations. Every graph follows a kind of a similar pattern. The idea is this: if we take our f of x function and we add k to it at the end, it's going to cause a vertical translation. So this is an example of a quadratic. So we do plus k here, it goes up that many k units. The other option is if I go minus k, it's going to go down that many units. Horizontal translations are caused by if I take the input x and I either subtract h or add h to that one. So here's an interesting one. When I did plus k here, that went a positive direction, so it went up. But if I do minus h, that's actually going to go to the right. It does the opposite in there. So when I take the input, I subtract by h, it's going to move it to the right. If I end up adding by h, it moves it to the left that many units. Okay, so here's a few ways that we can look at that. We'll kind of look at some examples of these here, but bottom line is, here's how I transform my quadratic horizontally and vertically, and that's to the parent function y equals x squared. Here's my cubic function. Again, same thing happens there. A lot of these have the same exact patterns to them. Okay, even with the reciprocal functions can follow the same idea as that. Here's my reciprocal function. I can do x, my input minus h. A does its own job. We're not going to worry about that just yet. We'll talk about that later. Okay, so, we'll talk about it right now. So A causes a stretch or compression. Okay, so if A is greater than 1, you get a stretch by that amount of factor. So if it's like A equals 2, it's a vertical stretch by 2. If A is in between 0 and 1, it compresses it. Okay, so it does something like this. If I have a quadratic, it's going to go like that, it flattens. Okay, anytime A is less than 0, we actually get a reflection over the x-axis. Okay, we just talked about what h and k have done too. So we'll get to those as examples right here. Okay. Okay, so sorry about the pause there. So we're going to use the graph f x equals x cubed to graph the function g of x equals 3 times x plus 1 to the third minus 2 and describe the transformations. Here's what I'm looking at for each of these values. We have, this is going to be my h, this is my k, and then this is my a. So as we looked at before, a is equal to 3, which is greater than 1. So I'm going to get a vertical stretch. Okay, h, it's a positive 1 there. So because we're looking at this as x minus h, technically speaking, h is a negative 1. So that's going to give us a horizontal translation. Oops. Okay, and more specifically to the left on this case. K is a negative 2. So that's going to give us a vertical translation. Okay, so if we look at the function f of x equals x cubed, let's just do a very rough sketch of that here. Try that again. Okay, So this is going to be my rough sketch of my y equals x cubed. So we're going to get, let's do it in blue. Horizontal translation left 1, vertical translation down 2. So we can go left 1, down 2. So this point right here is now going to be here. Instead of where it's at right here, we're going to stretch it. So we're going to give it just kind of a rough idea. It's going to look something like this. So it's a little bit skinnier, basically like that one. Okay, so again, that's just my rough sketch of that one. To confirm it, let's use Desmos. And here it is here. I'll turn this one off. There's my parent function. We see that this one is moving to the left. From this point here, it's going from left, it's going down here. Yep, right to that spot. Okay, and it's just a little bit skinnier there compared to the other. All right, so that's our transformation. So again, jobs of A has two jobs. It can either reflect it over the x-axis and or stretch it or compress it like that. H is going to cause horizontal translations. V is going to, or K is going to be a vertical translation. Okay, so we look at these two functions here. We want to describe how f of x becomes g of x, basically. So f of x is my square root function. We're going to write an equation for it once we figure out the transformations. So the biggest key is look at this point here and compare the two. We see that as a horizontal translation to the left one. Okay, so we got a left translation by 1. It's also taking this shape and flipping it over the x-axis. So now it looks like this. So we get a reflection. So we get two things. We are going to, right here, the graph is translated 1 unit to the left, and it is reflected. Okay, so before I get to that, that means I'm going to turn that into my g of x function. Because of the reflection, it's going to be a negative in front of the square root. It's moving to the left, so that's going to be an x plus 1 on the inside. So there's my g of x function there. Okay, remember, horizontal translations are going to be the opposite value of what goes in the function like that. Okay, identify the parent function f of x of g of x equals negative the absolute value 4 times x, and describe how the graphs are related. Okay, and then graph them on the same axes. So in this case, we look at this, we know that the parent function f of x needs to be just the absolute value of x. Okay, so when I look at how this is going to change, we have this negative sign is going to reflect it. So we have a reflection over the x-axis. Okay, and we also have this 4 being multiplied in there. Okay, so that 4 is going to cause just like any, like basically like the a value. I'm not affecting the x, the input by adding or subtracting. I'm also not adding or subtracting anything at the end. So this is basically going to cause our vertical stretch. Okay, so now we have those two things. Let's take a look at how that looks on the graph. So here we have parent function. We have a vertical stretch. So technically it's kind of doing it. I could do it like right here. We stretch it first, and then we take that and flip it over for g of x. Okay, so that's our absolute value function for its transformations. Okay, and that is actually going to be it for today. So again, a lot of these are following the same patterns. We're just trying to make sure we understand how to describe our transformations. A does the two jobs. It can do stretching, compressing, but it could also do reflecting if it's a negative value. And those are going to be two independent things. So if you look at this one specifically, this technically could have been like a -4. Okay, it's very similar to if I just did this, g of x equals -4 times the absolute value of x. Okay, they'll end up doing the same exact thing. It reflects and stretches. So that 4 causes the stretch, the negative causes the reflection. Okay, h and k can cause horizontal and vertical translations. So just make sure that you are understanding that k goes the same direction and h is going to go the opposite direction. All right, that's it for today. Take care.